Thanks, Sasha, for the introduction. Hi, everyone. Yeah, so today I'm going to tell you about fast matrix multiplication. So here's the graph of the best known exponent of matrix multiplication over time. So the best known number omega over here, such that we know how to multiply n by n matrices in n to the power of this exponent omega operations or time. Yeah, and you can see sort of at the beginning, there was sort of a lot of progress, especially around here. And then since then, it's been mostly flat, except for a few little improvements. So my goal for this talk is to sort of tell you about, first of all, how these algorithms are designed and what all the neat ideas that go into them. And second of all, talk a little bit about why is it that we've been basically stuck for like 35 years at this point, and why has this line become mostly flat? Okay, so here's more specifically the outline. So I'll start by introducing the problem of matrix multiplication, and I'll tell you about lots of different applications that it has throughout computer science. Then I'll get specifically into how matrix multiplication algorithms work, starting with Strassen's algorithm, and I'll tell you about some of the big ideas from the graph I just showed. And then I'll tell you a bit about our new fastest algorithm for matrix multiplication that I recently designed with Virginia Vassilevska Williams. And our new algorithm comes from improving a key technique that's used in these algorithms called the laser method. So I'll tell you about what that is and how we improved it. Then after that, I want to get into talking about barriers for even faster algorithms. So this is a more like complexity theoretic result where we rule out many approaches to designing faster algorithms. So it kind of helps to explain why we've been stuck, because there's a big, I'll show you there's a big barrier for the approaches we've been using. And it also is a way to sort of help narrow in on what types of algorithmic techniques could be helpful in the future. Okay, so let me start by introducing the problem. So I'm talking today about fast matrix multiplication. So you're given as input two n by n matrices x and y, and your goal is to compute their product. So here's the definition of matrix multiplication. If you don't remember, the way you should think about it is it's just for every I, which is a row of the first matrix, and j, which is a column of the second matrix, your goal is to compute the ijth entry of the product is the inner product between the ith row of the first and the jth product of the second. So your goal is to compute all these n squared different inner products between rows and columns of these matrices. And matrix multiplication really has applications throughout computer science. And I think one of the most exciting parts is that it's used to speed up problems, like lots of problems that involve matrices are clearly related to matrix multi in some way, but also a lot of problems that, especially at a first glance, seem like they have nothing to do with matrix multiplication. Somehow you can still speed these up by reducing to matrix multiplication. So let me give some examples. So first of all, pretty much, or many different tasks you can think of in linear algebra, you can do in the same amount of time as multiplying matrices, like computing the determinant of a matrix, or computing the inverse of a matrix, or solving a system of linear equations. You can do these all in about the same amount of time as matrix multiplication. Matrix multi is also used a lot in optimization. And for example, there's a very cool, pretty recent result, which says that if you have a linear program with n variables and a linear number of constraints, you can actually solve that linear program just as fast as you can do n by n matrix multiplication. And we similarly know how to, in addition to just linear programming, we can also do like semi-definite programming and other optimization problems, all by reducing to matrix multi. So matrix multi is really the bottleneck for a lot of different optimization frameworks. Matrix multi comes up a lot in graph algorithms. So one nice example I figured I should show you in case you haven't seen it before is you can actually detect whether an n-node graph has a triangle in about the same amount of time as it takes to multiply n by n matrices. And the idea is that if you make the adjacency matrix of your graph and you compute it square. So you multiply it by itself to compute it square. Then the entries of the square are now telling you, the like ijth entry is now telling you how many paths of length 2 are there from I to j. So there's a triangle if there's an I and j which have a path of length 2 and also a path of length 1. So to figure out, once you have the square, you can just iterate over all the edges and check whether there's also a path of length 2. And that tells you if your graph has a triangle. So you can find triangles in the graph in the same amount of time as matrix multiplication. But similarly, matrix multi is used in lots and lots of different graph algorithms in more general subgraph finding. It's used in the fastest algorithms for like all pair shortest paths, for the traveling salesman problem. Almost every area of graph algorithms, you can speed up some problems using matrix multi. And then matrix multi comes up a lot in scientific computing, like linear equations and systems of linear equations really naturally model a lot of scientific phenomena. And matrix multi comes up when you're trying to figure out what's going on in these complicated systems. It comes up in parsing algorithms, like when you're designing compilers and interpreters, like the best algorithm for context-free grammar, for parsing context-free grammars uses matrix multi. You're probably all familiar that matrix multi is used throughout modern machine learning, training and in evaluating models. And there's even more examples I didn't put on this slide, like it comes up a lot in graphics and in databases and so on. So matrix multi really shows up in a lot of different areas, and being able to do it quickly is really important for speeding up a lot of different algorithmic tasks. And a really nice fact, especially in light of all these different applications, is that we have really fast algorithms for multiplying matrices, both in practice and in theory. So, in practice, a lot of engineering work has gone into like optimizing all the little details of matrix multi algorithms and designing like fast distributed systems for multiplying matrices quickly and so on. But on the algorithm side, a lot of work has gone into designing fast matrix multi algorithms as well. And that's what I want to tell you about now. Okay, so just to remind you again, so our goal is to multiply two n by n matrices x and y, and n is going to be like the side lengths of these matrices throughout this whole talk. And you can think of these as matrices whose entries are real numbers or complex numbers or integers mod 2, or like they can come from whatever ring or field you want. But the way I'm going to measure the running time of our algorithm is in terms of the number of arithmetic operations that the algorithm does, the number of additions and subtractions and multiplications and divisions of numbers that it does. So normally when you want to figure out the running time of your algorithm, the details of like exactly what the entries of your matrix are can also be very important. Like you can imagine if there's really, really huge numbers in your entries, it can take a lot of time just to read and multiply those numbers, which is sort of unrelated to the matrix multiplication part. So roughly the real running time should be like the number of operations times how much time it takes to actually do each of these operations. But I'm going to abstract this detail away and just count the number of arithmetic operations today. So the main like yardstick for measuring how fast these algorithms are is called omega, or the exponent of matrix multiplication. So it's the smallest exponent such that you can multiply n by n matrices in roughly n to the omega operations. So for example, the most straightforward algorithm if just following the definition of matrix multi shows that omega is at most 3. There's n squared different output entries, and for each one you take the inner product of two vectors of length n, which you can do in O of n operations. So in total you get O of n cubed operations, which shows omega is at most 3. And then this straightforward, as we were sort of talking about before, this straightforward algorithm was really believed to be optimal for a while, until in 1969, Strassen gave this big breakthrough algorithm where he showed that actually omega is at most 2.81. So you can multiply n by n matrices in n to the 2.81 operations. And then since then, there's been a lot of work on the problem that was sort of shown in the graph I showed on the first slide, leading up to the best known algorithm today, which comes from this recent joint work with Virginia Vassilevska Williams, where we showed omega is at most 2.37286. Okay, so there's a question?
Yeah, I just said a small question. What is the best known, like practically, the best practical implementation of the omega? Do you know?
Oh, yeah. That's a great question. Yeah, I'll talk about it a little bit more later, actually. But this Strassen's algorithm is used. Strassen's algorithm is used in practice. The algorithms after Strassen's algorithm have not, to my knowledge, actually been some of them have been implemented, but they're not actually very effective in practice because of big constant factors. Yeah.
Okay.
Okay, so this is the best known algorithm. The best known bound is 2.37286, and it's actually popularly conjectured that omega is equal to 2. And this would be really amazing if it's true. So remember, these are n by n matrices we're multiplying. So it takes n squared time just to read in the entries of the input matrices and write out the entries of the output matrix. So if omega is 2, that means you can multiply n by n matrices in roughly the same amount of time as it takes just to read them in and write them out. And especially in light of all the different applications of matrix multi, this would be a really nice and powerful result. And it's popularly conjectured as true, but we don't yet know the algorithmic techniques needed to achieve that. Okay, so let me tell you about how these fast matrix multiplication algorithms work. In fact, they all work in the same general way. So they all work by using an algebraic identity to efficiently solve a small case of matrix multiplication, and then using a recursive approach to use that to solve bigger and bigger instances of matrix multiplication. So for example, let's say we wanted to use 2 by 2 matrix multi as our small case. Well, the straightforward algorithm for 2 by 2 matrix multi uses 8 multiplications. There's of numbers. There's 4 output entries, and each one you're taking the inner product of 2 vectors of length 2, which requires 2 multiplications of numbers to compute. But the key behind Strassen's algorithm was that he showed you could do 2 by 2 matrix multiplication using only 7 multiplications of numbers. So here's what his identity looks like. The details are not important at all, but you can just see on the left, he somehow does only 7. So he takes in as input the entries of at 2 by 2 matrices x and y. Then he somehow does only 7 multiplications of numbers, and then using just a lot of additions and subtractions, he's able to recover the output entries of matrix multiplication at the end. So once he has this algorithm for 2 by 2 matrix multi, then he uses a recursive approach to multiply n by n matrices. So to multiply these bigger matrices, what you do is you block them into n over 2 by n over 2 blocks. So you think of each as a 2 by 2 matrix where each entry is itself an n over 2 by n over 2 matrix. And then you just plug those blocks into Strassen's identity, which shows you how to recursively do only 7 multiplications of these smaller n over 2 by n over 2 matrices in order to multiply n by n matrices. And it does a lot more additions and subtractions of these n over 2 by n over 2 matrices than the straightforward algorithm. But fortunately, we know it's very easy to add and subtract matrices. It takes just n squared time to do that. So really the slow step in the recurrence ends up being the multiplications, and going from 8 to 7 ends up giving a big improvement. So the recurrence you get is the time to multiply n by n matrices is 7 times the time to multiply n over 2 by n over 2 matrices plus order n squared time to do just additions and subtractions of matrices, which we solved this as we learned in algorithms class, and you find that you can multiply matrices in n to the 2.81 time. So omega is at most 2.81. And in fact, I mentioned this before, but actually every algorithm in the history of fast matrix multiplication algorithms is also of this general type of form, where you get an identity for multiplying some particular fixed size of matrices, and then use it recursively to multiply bigger and bigger matrices. And there's really nice theorems that if you had any say, arithmetic circuit for multiplying matrices, you could always actually convert it into a recursive algorithm like this that only loses like a small constant factor in the running time. So you can actually assume without loss of generality that all the matrix multiplication algorithms we're dealing with have this recursive form to them. Okay, so what do we know about how many multiplications you need to multiply matrices? Well, so Strassen's algorithm I just told you about, it showed that you can multiply 2 by 2 matrices using 7 multiplications of numbers, which gave omega z was 2.81. So the first improvement on Strassen's algorithm came about 9 years later by Pon, and he showed that you can multiply 70 by 70 matrices using 143,640 multiplications of numbers, which results in a bound on omega of 2.80. So yeah, so this is okay. This was actually still pretty surprising because it took almost 10 years since Strassen's algorithm to figure out that we could improve on it at all. And like in light of all the applications of matrix multiplication, even small improvements like this are really important to figure out, to try to figure out what is and isn't possible in this area. But at the same time, Pon's algorithm really showed that like these algorithms become really unwieldy really quickly. Like I showed you Strassen's identity, and I think it already looked kind of complicated. You could just imagine what Pon's identity looks like. So later work after Pon's started using a more indirect approach to designing these algorithms. Instead of directly giving identities for doing matrix using fewer multiplications, it used a more indirect approach. So let me tell you about that. So the indirect approach that was used by all the algorithms since Pon's algorithm, it involves two main components. So the first is that you start with a different algebraic problem P other than matrix multiplication that we have an efficient algorithm for. So you start with a different problem that we know how to solve quickly. And then you show how to reduce matrix multiplication to your problem. So usually in theoretical computer science, reductions are like a tool for showing hardness. Like you show A reduces to B, that means B is at least as hard as A is. But here we're using it as an algorithmic tool instead. So we start with a problem P that we can solve really fast. And then by reducing matrix mult to P, we can solve matrix mult really fast as well. That's the idea. So okay, let me tell you a little bit more about what I mean by, so like, first of all, what's an algebraic problem? So the algebraic problems I'm talking about are problems where you're given as input a bunch of numbers, and your goal is to evaluate a prescribed set of polynomials at those numbers. So for example, matrix multiplication itself is an algebraic problem. Like in 2 by 2 matrix multi, you're given as input 8 numbers, like the entries of the 2 by 2 matrices. And your goal is to evaluate these 4 polynomials that appear as the 4 output entries of 2 by 2 matrix multiplication. So matrix multi itself is an algebraic problem, but you can imagine like crazy different looking algebraic problems also. Like here's another example of a problem I'll call P, where in this one you're given as input these 10 numbers and your goal is to evaluate these 5 polynomials. So in general, this algebraic problems look like this. You're given as input numbers and your goal is to evaluate some polynomials. You've probably seen other examples too, like polynomial multiplication is an example where you're given the coefficients of 2 polynomials and you want to figure out the coefficients of their product, or things like Fourier transforms and things like this can also be viewed as algebraic problems. But anyway, so these are the problems I'm talking about. And then what do I mean by a reduction? The notion of reduction that I'm going to use today, and in fact that all the best known algorithms for matrix multi use, is actually a really simple notion. So we'll reduce from a problem P to matrix multi by just removing some of its inputs and some of its outputs to turn it into matrix multiplication. So let me give you an example with this problem P I wrote over here. So let's pretend we had a really, really fast algorithm for solving this problem P. So we have some black box that you put in these 10 numbers and it really quickly outputs these 5 numbers. And we want to use this for solving 2x2 matrix multiplication. So one thing we can notice is that somehow these variables x33 and y33 maybe don't seem so useful to us. So we're just going to remove them. And you can imagine when we use our black box for solving P, whenever it asks us what's the value of x33 and y33, we'll just always use 0 for their values. So then wherever they show up in the outputs, they're just going to go away because we always plug in 0 for them. And similarly, maybe this last output polynomial doesn't seem so helpful. So we're also going to just ignore it. And you can imagine when our black box will spit out 5 numbers, and we'll just ignore one of those numbers and only use the other 4 of them. And once we've done that, you can see here, I've actually turned my problem P into 2x2 matrix. Well, like you can see, this first polynomial is the top left entry, and the second one's the top right entry, and so on. So here, by doing this simple reduction where I just removed some inputs and outputs, I turned this problem into matrix multi. And if we had a fast algorithm for solving P, then it would give us a fast algorithm for matrix multi. But this is just a toy example. Typically, the problems are much more complicated and don't start off looking so much like matrix multi in the first place. So researchers have developed some methods for finding reductions like these in general between algebraic problems. And these methods are the subject of our new improved algorithm. So there's a specific method that's used by the best known algorithms that's called the laser method for finding these reductions. And our new algorithm is a way to improve the laser method. Okay, so like I said, so matrix multi algorithms, they have 2 main components. They have some algebraic problem that we have an efficient algorithm for, and we have a method for converting or reducing it to matrix multiplication. So Strassen's algorithm can kind of be seen like this, but Strassen sort of directly gave an efficient algorithm for 2x2 matrix multiplication. So he didn't need to use any methods. Since Strassen's work and Pon's work, there's been a lot of results on improving both the problems and the methods, leading up to the seminal work of Coppersmith and Winograd in 1987. So they introduced a problem called the Coppersmith-Winograd tensor, or the Coppersmith-Winograd problem, and they showed that this problem has it's like kind of a weird problem. They showed it as a really efficient like linear time algorithm for solving it. And then the method they used to convert into matrix multi is called the laser method. It was called this by Strassen actually, and then Coppersmith and Winograd improved on Strassen's implementation to use it in its current form. And using that, they proved the bound of 2.376 on omega. Then all the improvements since then, before ours, so continued to use the same laser method as the method for converting problems into matrix multi. And what they did was they found that if you take higher, well, so-called Kronecker powers of the Coppersmith-Winograd problem, then the laser method's able to get better and better algorithms out of it. So very roughly, when you take a higher power of this problem, it becomes bigger and more complicated and harder to analyze, but the result at the end gets a little bit better. So it becomes, as the power gets larger, it becomes like quite computationally difficult to actually apply the laser method to the problem. But you can see you get better and better bounds on omega as you do this. Okay, and then in our new algorithm, we use the same power of the Coppersmith-Winograd problem as the previous algorithm, but we give the first improvement to the laser method since it was introduced back in 1987. So our new method finds more efficient reductions between algebraic problems, so we can use it to convert Coppersmith-Winograd into a bigger, better matrix multiplication problem to get a better algorithm. And okay, one thing I guess you've probably noticed is, numerically, our algorithm only improves a tiny little bit on the previous one, which in turn improved a tiny little bit on the one before that, and so on. So this is a phenomenon I'll talk more about a bit later in the talk. But I think the interesting part of our algorithm is not necessarily the numerical improvement, but rather, so the laser method is really like the most general way we know to reduce between algebraic problems. And so like in the future, if someone came up with a different problem other than Coppersmith-Winograd to use as the first component of a matrix multi algorithm, then our improved laser method would also be able to get a better algorithm out of that. So it's like it's a generic improvement and not just somehow specific to this Coppersmith-Winograd problem. Okay, so let me tell you a bit more about the laser method. So like I mentioned, the way the laser method works is its goal is to reduce some problem P to matrix multiplication. So it takes in as input at the top an algebraic problem P that we have an optimal algorithm for. And then it involves a lot of different steps where you like remove away parts of P. Remember, we're sort of removing inputs and removing outputs for it. I like to think of it a little bit like sculpting, where you like start with a big block and your goal is to get to a nice, sculpture of matrix multiplication at the end, and you keep chiseling away parts that don't look like matrix multiplication until you get to a matrix multi at the end. And your goal is to get to as big a matrix multi at the end as possible. So like there's all these steps where you carefully remove like extra variables and polynomials until you get to a matrix multi. So I want to tell you a little bit about our improvement, which fortunately is, well, the laser method itself is quite complicated, but actually our improvement is confined to one step near the end, which is quite simple. And I can actually show you the main idea behind it. And the idea is to take a step that used to be, sculpting away parts of the algorithm, parts of polynomials in some greedy approach, and instead using a more clever probabilistic method to find a bigger matrix multiplication. So let me tell you a bit more about that. So here's like the subproblem that's solved by this step of the laser method that we improved. So in this problem, you're given as input a polynomial that looks like this. So it first has m terms that are just like degree 3 monomials that don't share any variables at all with each other. And these are, I'll call these good terms that don't share any variables with each other. And then also s times m, I'll call junk terms that just like use some of the variables from our good terms, and like x1, y2, z3 uses variables from our first 3 good terms, for example. And the goal in this subproblem is that we want to reduce from this polynomial to a single polynomial that only has good terms. So our goal is to pick some of the variables in this polynomial and remove all the monomials containing them, like by setting them to 0, so that all the junk terms are removed. And we want to leave as many good terms at the end as possible. So like removing the junk terms will probably, like, unfortunately along the way, remove some of the good terms as we're setting variables to 0, but we'd like to leave as many of them as possible. So for example, here's a polynomial here, m is 3, and I guess s is 2/3 because there's 2 junk terms. In general, you should think of m and s as both like pretty large numbers. So in this example, if we set x2 and y2 to 0, then, well, this is what we get, where I just put in 0 for all the x2s and y2s. So it makes both of the junk terms go away, and it made one of the good terms go away as well. So we got at the end 2 good terms out of this. And the question is, in terms of m, the number of good terms, and s, the like ratio of junk terms, how many good terms can we keep? So what's in the worst case, how many good terms can we keep when we do this? And so the previous uses of the laser method, when they were solving this subproblem, they at the end kept m divided by s of the good terms, and our improvement improves it to m divided by square root of s of the good terms. So we show a new way to choose which variables to set to 0 that keeps more of the good terms. So here's the idea. So So the old approach is a really natural, greedy approach to solving this problem. So what you do is you just repeatedly pick a good term that shares variables with the most junk terms, or sorry, the fewest junk terms. So because there's like m good terms and s times m junk terms, you can always pick a good term that shares variables with order s of the junk terms. And we'll just zero out all three of the variables in this one good term to remove all of those junk terms. Oh, I'm sorry. I wanted at least S junk terms, not at most S junk terms. So you pick the good term which shares variables with the most possible junk terms, and then you set to 0 the variables in that term. So you remove at least S junk terms each time you do this. So this will remove like at least S good term. Sorry, I'm confusing myself. Okay. 0 variables to. Oh, okay. I'm sorry. I've been explaining this wrong. So to start, you pick a good term that you want to keep. Okay, we're going to pick a good term that we want to keep at the end. This good term will share variables with at most order S junk terms. So we'll pick the good term that shares variables with as few as possible junk terms. And by an averaging argument, this good term will share variable with at most order S junk terms. Okay, now we want to remove those junk terms so that we now have this one good term that doesn't share variables with any of the junk terms. Okay, so to do that, in each of the junk terms, we'll pick one of the variables it has, which doesn't share with our good term we picked, and set it to 0. So this will remove about S good terms for each one that we keep. So we pick one we want to keep. We set a variable in each of the S junk terms to 0, but this can remove S of the good terms as well when we did that. So for each one good term we keep, we remove S good terms. So at the end, it will result in M divided by S good terms that we keep. Yeah, sorry, I made that more complicated than it needed to be. But it's just like the greedy approach you could imagine for this problem. So our new approach to doing it faster instead uses the probabilistic method. So what we show is that if you pick M divided by square root of S of the good terms at random, and just zero out every variable that's not used by the good terms you've picked, then this will remove all the junk terms with some small but non-zero probability. So if you just pick M over root S good terms at random and we put to 0 every variable that's not used by those, then all of the junk terms will actually go away with some probability. And so by the probabilistic method, there has to exist a way to pick M over root S good terms such that you could keep all of those while removing all of the junk terms. That's the idea behind the improvement. So it's a slightly more clever way to choose which good terms to keep. Okay. So that's our improvement to the laser method. And I'll actually talk a little bit more about it later as well. But I want to move on to the second part of my talk. We're talking about barriers for even faster algorithms for matrix multiplication, or what is needed to design faster or optimal algorithms for matrix multiplication. So if you haven't seen a barrier result before, these are kind of common, I think, in complexity theory. The idea is that, well, at least in this case, our barrier result is a no-go theorem for improving the matrix multiplication exponent omega. So what we show is that if omega is equal to 2, which is popularly conjectured, then the algorithm to achieve that has to look very different from the current best approaches to designing matrix multiplication algorithms. So it sort of helps to address the question, why is it that we're stuck at like 2.373 and not at 2, and we haven't gotten to 2? Like, the answer is that if we really want to get to 2, the algorithm has to look really, really different from the algorithms we've been designing up till today. And so this is like, in some sense, a negative result. Like, if you're a fan of fast matrix multiplication, this might be a sad result for you. But barrier results can also be helpful at sort of narrowing in the focus of algorithm designers to help find techniques which could lead to faster algorithms. And I'll talk more about this soon, but we actually used our barrier result to help find our improvement to the laser method and help speed up matrix multiplication. So I should mention.
Do you have candidate techniques for like like you just showed that, hey, this technique that you use right now doesn't work. If you want like omega equal to 2, then do you have like candidate other techniques that you could use? Like,
Yeah. The short answer is not really, but it'll be easier for me to tell you about it a couple slides from now. So let me return to that
okay.
question in a little bit. Yeah, that's a great question. Yeah, the answer is a kind of unfortunate one. Okay, so I should mention before I get into this that we're not the first people to notice that we're kind of stuck on matrix multiplication and ask why is that. And there's a lot of nice prior work that ruled out some specific approaches to designing matrix multi algorithms. Like there's this nice paper by Alman, Spielka, and Umans about ruling out like there's like a particular conjecture in Coppersmith-Winograd's original paper that could imply omega is equal to 2. They ruled that out. There was a nice work by Ambinus, Filmus, and Legal that ruled out sort of the current implementation of the laser method. So they sort of the exact laser method we have now can't prove omega is equal to 2 without some really big changes to it. There's a nice line of work by Blasiak et al. About ruling out this different approach to designing matrix multi algorithms called the group theoretic approach. So they should show some barriers to this type of approach. But compared to these, I think our barrier that I'm going to tell you about now is a bit more general. So it rules out sort of not only these approaches we know about already, but it also aims to rule out very general classes of approaches and even like sort of techniques that we can dream of and don't even have any idea how to make use of for designing matrix multiplication algorithms. So let me tell you more specifically what it says. So remember, algorithms for matrix multiplication, they have 2 main components. The first is some problem that you can solve efficiently, and the best algorithms for the past 30, 40 years have used the Coppersmith-Winograd problem. The second component is a method for converting these problems into matrix multiplication. And the best algorithms, again, for the past 30 years have used this laser method to do this. So what we do is we first define big generalizations of these 2 components. So on the left, we've defined a large class of problems that generalize the Coppersmith-Winograd problem. And it includes problem with shared combinatorial properties with Coppersmith-Winograd, like, this many variables appear this many times, or like these variables don't appear in the same monomial together or something like this. And it also includes problems that share algebraic properties with Coppersmith-Winograd, like I won't get into too much detail about that, but like problems which can be degenerated from tensors that come from certain algebraic structures and things like this. So there's sort of combinatorial and algebraic properties that this CW problem has, and we define this large class of problems that share any of these properties with CW problem. Okay, that's the first class. And then the second class is we generalize the laser method. So we call this, the universal method. So remember in the laser method that I've been talking about, we take a problem and you set some variables to 0 to turn it into matrix multiplication. But you can imagine more generally, there might be better ways to change different variables to 0 to turn into a bigger matrix multi. And moreover, you can imagine other types of ways to reduce between polynomials also. Like you could imagine like substituting in expressions for variables, like setting x1 is equal to x2 plus x3 instead of just setting x1 to 0. Or there's even in algebraic complexity theory, we have a really general way to reduce between problems that's called a degeneration. And our universal method even includes this most general way that's known to reduce between these types of problems. And then what we prove is that there's no way to achieve omega is equal to 2 by using any problem from the left combined with any method that falls within the universal method. So if you start with any problem that shares any of these properties with the Coppersmith-Winograd problem that we've been using for the past 30 years, and combine it together with any method for reducing between problems, even the most general methods that we know in algebraic complexity theory, there's no way to achieve omega is equal to 2 like this. And the specific numbers sort of depend a little bit on the details, but for one example, if you want to use Coppersmith-Winograd problem itself combined with any method within the universal method, you can't beat 2.18 for the exponent of matrix multiplication. So if you want to get all the way to 2 or even beat 2.18, you really have to do something very different looking for at least one of the two components for designing these algorithms. Okay, so let me give you an idea of how we prove the barrier. I think it's actually a really cool proof. So the idea is to take a complexity measure for algebraic problems called slice rank. So slice rank is some measure of how complicated a problem is. And we show that slice rank has 3 key properties. So first, we show that Coppersmith-Winograd problem has small slice rank. So according to this measure of how complicated a problem is, Coppersmith-Winograd is actually not a very complicated problem. Okay. Second, we show that universal methods reductions never increase the slice rank. So if you start with a problem of small slice rank and you use one of these very general reductions to turn it into a new problem, then the new problem also has to have small slice rank. And then the third component is that matrix multiplication itself actually has large slice rank. So matrix multiplication is actually very complicated for this measure called slice rank. So these 3 together actually just imply the barrier, because if you had an algorithm for matrix mult that you designed by taking Coppersmith-Winograd and somehow using the universal method to reduce it to a matrix mult problem, turn it into a matrix mult problem, then the reduction has to result in something that has small slice rank on the right-hand side, and thus it has to be a really small instance of matrix multiplication. Whereas generally our goal to design faster algorithms is to reduce it to a really large matrix multiplication. Yeah, so that's the idea behind the proof. So let me say a bit more about slice rank. Slice rank is actually a little bit related to our improvement to the laser method that I told you about before. So I want to give a couple of details about that. So first, what is slice rank exactly? So it's a measure of complexity for a trilinear polynomial. So these polynomials, like the ones I showed before, where each monomial has like one x variable, one y variable, and one z variable in it. Oh yeah, sorry, there should be some coefficient here also, not just the sum of all these monomials. So we say that a trilinear polynomial has slice rank 1 if it can be written in one of these 3 forms. So we say slice rank 1 if it's some polynomial in just the x's times a polynomial in the y's and the z's, or a polynomial in just the y's times a polynomial in the x's and the z's, or a polynomial in just the z's times a polynomial in the x's and the y's. So for example, here is a nice trilinear polynomial with 4 monomials, and we can see that it can be written in this way as just x1 minus x2 times some polynomial in the y's and the z's. So that shows that this example polynomial has slice rank 1. Okay, and then more generally, the slice rank of a polynomial is the minimum k, such that you can write it as the sum of k different slice rank 1 polynomials. So slice rank is asking how many of these slice rank 1 polynomials do you need to decompose your input polynomial. And one of the components of the proof that I mentioned before is that universal reductions never increase the slice rank. And in the case of just setting variables to 0, like the reductions we've been talking about, it's pretty easy to see that that's the case. So if p has slice rank k, and you reduce from p to q by setting some of the variables to 0, then q is also going to have slice rank at most k, right? Because like you can imagine here, if you just took one of these slice rank 1 polynomials and set some of the variables to 0, it's still going to be a slice rank 1 polynomial by just like setting to 0 inside these 2 components of the polynomial. So it's clear in the case of just setting variables to 0 that slice rank can't increase when you do a reduction. And in fact, you can show even for these more general types of reductions, slice rank can't increase when you reduce from one problem to another. So that's the idea. And then let me quickly mention, slice rank is actually comes up quite naturally in the laser method. So the polynomials I was talking about before, which are like a sum of m good terms, so like these terms that don't share any variables with each other. One thing you can show is that this polynomial has slice rank m. So there's no way to decompose it into a smaller than m number of, like each monomial just naturally has slice rank 1. And you can show for this polynomial where no two terms share any variables with each other, that this actually has to have slice rank m, and there's no way to get smaller slice rank with it. So earlier, when we were talking about this problem of taking one of these polynomials with m good terms and s times m junk terms, and setting some variables to 0 to get rid of all the junk terms, and asking how many good terms you could be left with at the end, we saw you could be left with m divided by square root of s good terms. And this kind of gives us slice rank lower bound for the problem p, polynomial p also. So if we get to m divided by square root of s good terms by a reduction, which can't have increased the slice rank, that means p itself had to have m divided by square root of s slice rank at the beginning. So if you can show slice rank upper bound on a polynomial, show that it's not too complicated and has pretty small slice rank, that kind of limits how big of a good polynomial you can reduce your problem to. So if the slice rank is small, then you know that no matter what you do to get rid of the junk terms, you're going to be left with only a small number of good terms at the end. So that's maybe some idea of the connection between slice rank and the laser method, our improvement that I told you about before. Okay, so I want to finish on a more optimistic note, I guess. So, even though this barrier, if you're someone who really wants to prove omega is equal to 2 and really wants to design fast matrix-mole algorithms, this barrier might seem like a sad result. Barriers can also be helpful to designing faster algorithms. So like a simple observation is that we now know what techniques to avoid when we're trying to prove omega is equal to 2. And it can help to focus our attention on techniques that might be more effective. But even if you don't want to go all the way to 2, you can also try to find ways to tighten the barrier. Like our best upper bounds are only like 2.38, whereas the lower bound I just mentioned is only like 2.18. And you could try to close the gap and actually design somewhat faster algorithms for matrix multi. And in fact, this idea helped to lead to our new faster algorithm. So once you realize that this notion of slice rank is really important for studying these algorithms, you can look more carefully at the laser method. And we know that the laser method, since it's reducing between problems, it can't increase the slice rank. But if it actually decreases the slice rank, then you're like losing even more. Like you want to find a reduction that's not decreasing the slice rank or decreasing it as little as possible. And when you look at the different steps, we narrowed in on this step where the slice rank was decreasing quite a bit and showed how this modification could make it decrease the slice rank less. So like the idea behind the barrier actually helped us to narrow in on a part of the laser method that could be improved. And there's been also a lot of nice follow-up work on proving like different proofs of the barrier or extending the barriers to more kinds of problems, which are really nice because just extending it is nice because it helps us even more to avoid problems we might have wasted our time thinking about earlier. But I think different proofs are especially interesting because maybe they could give it like another perspective on the laser method and which parts of it could be further improved. Okay, so that's most of what I wanted to say. So I guess what's next in this area. Well, first of all, it would of course be very nice to design faster algorithms for matrix multiplication. I think it's not impossible to like find other ways to try to improve the laser method. And that maybe even the barriers I was just talking about could help us find parts of it that could be improved. It'd be also exciting to find a replacement for the Coppersmith-Winograd problem, find a different problem that somehow can be turned into larger matrix multiplications. But as I mentioned, I don't think we really have great candidates for replacing either of these. So we know like what to avoid, but I don't think we have great idea yet for what we should be doing instead. And that's sort of a big problem in this area right now. Yeah, and like I mentioned, I think it's nice to use barriers to inspire more progress, and possibly even try to prove more barriers and rule out other approaches to design these algorithms could help to design algorithms and vice versa further. And finally, well, someone asked a little bit about whether these algorithms are practical. And the one unfortunate reality is that the laser method, it's like a very intricate and complicated method for designing these algorithms. And it currently involves a lot of different steps, which really massively blow up the constant factors involved in the algorithm. So like I mentioned, the laser method has like 6 different steps. Basically, each of these steps blows up the constant factor of the algorithm quite a bit. But I think it would be really interesting to see if any of these different ideas that have gone into fast theoretical algorithms could be used to design more practical algorithms as well. And barriers might even be a nice lens through which to study this problem, to see if we could try to figure out more carefully if any of the steps have barriers and somehow require large constant factors, or if there are any that could be used in practice as well. Okay, and yeah, this is a comic that Zach Wienersmith of SMBC Comics drew. It's depicting me and Virginia presenting our new algorithm. Yeah, so I usually wear glasses when I'm not talking at my computer. So I think it's meant to be, poking fun at us. But nonetheless, over Zoom, I can't really see or hear you all, but I hope you're all reacting true to the comics.
Thanks, Josh. Can I ask a couple of questions?
Yeah, please.
So